Okay, I want to start this lecture out by saying that I put a non-comprehensive list of the reactions that we've done so far for electrophilic aromatic substitutions and nucleophilic aromatic substitutions and how to add different groups to the ring. It should be in the March 20th folder, so you have to see it if you got access to this video through Canvas. But what I want to do is kind of do some applications today, and you know, if you're an overly ambitious go-getter student who hasn't had this COVID-19 stuff beaten out of you, had the overly ambitious part beaten out of you, then what you could do is think about writing the product, or think about how we're going to do each one of these transformations, and kind of take them in sequence so that they're going to be a little bit more difficult than they are. And we'll see how far I get in the next 52 minutes. And if I don't quite get to all of them, then maybe those at the end will be left over for you as graded practice problems. But let's see how far we get. So let's start with this reaction of reacting this with HNO3H2SO4. So if you want, you can stop, write the product of the reaction, the major product or major products of the reaction, and you can check and see if you're correct. First step is to determine what is the electrophile. In this case, the electrophile is NO2+. The next question is, what kind of group is this activating, deactivating, ortho, para, or meta? Now, this is a little different because the oxygen is attached to the benzene ring. So if you saw the carbonyl and you said immediately it was a deactivating group, that's not correct. Instead, you have to look, and when the oxygen is attached to the ring, it acts just like a normal oxygen group. So this is going to be an activating ortho-para director, which means it's going to direct the NO2 to the ortho and the para positions relative to that group. So the major products of this reaction will be NO2 ortho and NO2 para. And again, I want you to write both products, the ortho and the para products, if it's an ortho-para director. Okay, so given that, let's go on to the next reaction. And what happens when we have two benzene rings attached to groups? So the question here is, what is the electrophile from Br2 and FeBr3? It's Br+. Now the question is, which ring will the Br+ add to? If you said the ring with the activated group attached, you were correct. So the carbonyl group over here is attached to the ring. That ring is going to be deactivated, whereas the oxygen that we just saw is attached to this ring. That's going to activate the ring, which is going to make it react faster. So I am going to add the bromine to the activated ring. The activating group then is going to direct ortho and para, so that the two products I would get for this reaction are going to have the NO2 group added to the ortho position, and then the NO2 group added to the para position. Okay. So when you have a ring, when you have this ring, two rings, you've got to figure out which ring is more activated, and that's where the groups are going to add. Okay, so let's go on to a third problem here. The third problem is going to be what will be the major product or products of this reaction. So I'm going to add another NO2 plus group to the ring. Which ring am I going to add to, left or right? If you said the left ring, you're correct. Why? Because both of these rings have another ring attached to it. But the bromine being on the right-hand ring means that it's going to be a little bit deactivated. So that means that the benzene ring on the left is the one that's going to get the NO2. Now, what is this ring now has another ring attached to it. Now, what is a benzene ring? It's an activating group relative to this ring right here. So it's going to direct to the ortho and the para positions. Now, we can invoke sterics here to say, you know what? It's not going to add in this position, because if you wrote out the structure of this molecule, which is actually called a biphenyl, that position is very sterically hindered. And so we would just actually get the para. We would just add the NO2 group to the para position. And then the bromine is actually para in that case. So again, in this case, it'll add to the left-hand ring simply because the right-handed ring is deactivated, relatively speaking, with the presence of the Br. Okay, so now what we want to do is now we want to talk a little bit about how would you prepare the remaining probably 6 molecules from benzene. And what you need to have is a strategy in order to add each group to the ring, but then we have to think about the sequencing in order to get the groups in the right orthometa or para positions. So in this case, I want to make this what would be called para-nitrobenzoic acid. So how would I add the nitro group? I add the nitro group by using HNO3, H2SO4. How do I add the carboxylic acid group? Well, this is where having that sheet, that list of reagents, there's a couple of ways we could add the benzoic acid. We could add a methyl group and then KMNO4 that, oxidize that to form the carboxylic acid. Or we could also add the carboxylic acid by adding the bromine, adding magnesium to make the Grignard, and then reacting the Grignard with CO2 to make the carboxylic acid. So there's 2 different ways to put the carboxylic acid on, and honestly it doesn't matter which one you use as long as you put the carboxylic acid group on the ring. Okay, now let's talk about the sequencing. We have a problem. Can you identify what the problem is in terms of writing this para disubstituted ring? If you said that this group is a deactivating meta-director and this nitro group is a meta-directing deactivated group, you would be correct. So how am I going to get these 2 things para? Well, let's look at our sequence of reactions and see, is there a group that I could add that would be an ortho-para-director, and then add the other group before I convert the first ortho-para-director into the final compound. And here's what I mean by that. Nitro, I'm adding one shot. So there's not another reagent that, or another group that I put on and convert the nitro group to. So it's going to have to go on last. But what about the carboxylic acid group? Where did it come from? It came from a methyl or a bromine. Now, methyl and bromine are both what? Ortho-para-directors. So you could say, you know what? I'm going to add the methyl group first. How do I do that? Methyl chloride, aluminum trichloride. That'll put the methyl group. And in all these synthesis problems, I like to put the group where it's going to be in the final product. So I know that I'm going to take that methyl group and I'm going to treat it with KMNO4 to give me the carboxylic acid. But what I want to do at this point is, since it's an ortho-para-director, now I'm going to say, you know what? Let's go ahead and add the nitric acid, sulfuric acid, to be able to put the nitro group on, and the methyl group is going to automatically direct into the the para position. Now, in these synthesis kind of problems, if you were to get both ortho and para products, you can ignore one of them and just go on with the product you want. That's perfectly legitimate. So in this case, yes, I would get both ortho and para products, but I'm only interested in the para product, so I'm just going to write that one down. Now I've got the nitro group in the correct position, so now I can say, okay, let's go ahead and use KMNO4 and heat, just like we did in lab. I'm going to oxidize the methyl group into a carboxylic acid, but now the nitro group is in the correct position. Okay. So if we take a step back here and we think a little bit about what did we just do? What we did was we had to put the group on. If we have a group like a carboxylic acid that is directing to the wrong position, we might have to put the second group on with the methyl group being present, and then in the second step, convert the methyl group after I've put that other group on to the carboxylic acid. So sequencing is important here. Now you could say, can you do this? Could you do this reaction another way? Well, yeah, I mean, you could. In this case, what I would do is you'd put the bromine on, FeBr3, to put the bromine in the proper position. Now the bromine is ortho-para-directing, so now would be a great time to put the nitro group on. Because the bromine will direct the nitro group to its para position. Then let's go ahead and add the magnesium to it. Make the Grignard. And then react it with CO2, and I'm going to put the then H plus H2O step in. So what I would end up making is that product. And with all these synthesis problems, there are multiple ways to accomplish them. And sometimes it requires, and some of them are straightforward. Some of them might be a little bit more complicated with more steps. This isn't diving. You don't get creativity points. You don't get more points for doing something more difficult. On the other hand, they're both equally correct. So all you have to do is just get to the final product without using any, without making the wrong product or using a reagent that doesn't work. Okay, basically think of each one of these steps as a letter, and if you have garbage steps, you can't spell anything. So you want to get the letters, the reactions in sequence. Okay. All right, so now let's go on to the next problem. So how would I do this reaction? Again, if you want to stop this and think about, okay, how am I going to do this reaction? Go ahead and do it, and then come back and see if you were right. Now, how do I put the CH2CH3 group on the ring? I'm going to use aluminum trichloride and ethyl chloride. How do I put the NH2 group on the ring? Again, you could consult your chart. Be really helpful if those reactions are in your head. But if I want to put an NH2 group on the ring, what do I have to do? I've got to put an NO2 group on it and then convert the NO2 group to NH2. Okay, and we'll come back with those reagents. Now, what's the big problem here? The big problem here is both of those are orthopara directors. So now I have to think about, okay, is there a way that I could, convert or put on a meta director and then change it over into the group that I want? And there's actually two ways to do that. So let's put the NH2 group on first. So if you want to think about it this way, I could convert the benzene ring to a nitrobenzene, convert and then now I need to stop here because the nitro group is going to direct meta. So now let's go ahead and let's put on, with the nitro group, let's go ahead and put on the ethyl group, and then let's convert the ethyl group into a NH2 group. So by stopping at the nitro group and putting the ethyl group on, nitro then absolutely directs the ethyl group to the proper meta position. Now all we would need to do is to fill out the reagents, which again, I would strongly recommend stopping for a minute and putting those reagents in. How do we convert the nitro to amine? Fe or Sn, HCl, and heat. You can work out the synthesis by just showing how you're going to accomplish, or what steps you're going to accomplish. You do have to go back in and put the reagents, though. You can't just leave the scheme without knowing the reagents. So there is another way to do this, because there's actually another two-step sequence to put an ethyl group on the ring. So let me just show you that there is more than one way to accomplish this goal. Maybe in this case what I want to do is I want to put a carbonyl group on the ring first. Carbonyl is meta-directing. Then put my nitro group on the ring. Then convert my nitro group to an amine. And then we have to remember, how do I convert this phenyl ketone to a ethyl group? So this would be another perfectly legitimate, okay, it's an extra 1, 2, 3, 4 steps. It's an extra step. Again, it's not diving. You don't get, more points for more difficulty. But these are both equally correct. So again, what reagents would I use to accomplish this set of syntheses? I would again strongly recommend go ahead and put those in, because you're going to have to in the future. We would start by saying, let's do Friedel-Crafts acylation. Nitric and sulfuric acids to put the nitro group on. Again, with the carbonyl directing to the meta position. Fe or tin, HCl, and heat to put the to convert NO2 to NH2, and then finally the reduction of the phenyl ketone could be done by zinc, mercury, HCl, and heat, or it could be done by N2H4, KOH, and heat. This is Wolff-Kishner. This is Clemenson. So again, with most of these problems, there's different strategies you can use. You have to know your reactions, though. And you have to think, okay, how am I going to work through these steps to get the groups on, but then how am I going to get them on in the right order so that way I can get the correct substitution on my product. Okay. All right, let's try another one. Again, if you think through this molecule, if you want to try it on your own, go ahead and do that. First step I would suggest is figuring out how you're going to put these different groups on. Again, the list of reagents and transformations will help you, but you need to know them. Okay, so let's just start with something like this. Let's say that I'm going to put the ethyl group on by Friedel-Crafts alkylation. How am I going to put the oxygen group on? Well, this is a guaranteed multiple step process. In order to put the oxygen on, I need to first of all put on a nitro group, convert the nitro group to an NH2 group, convert the NH2 group to a diazonium salt, convert the diazonium salt to an OH. In the lecture video that replaced Wednesday's class, we talked about taking the OH group and deprotonating it to form the alkoxide, and then reacting the alkoxide with an alkyl halide to give me the appropriate OR group. So that is 1, 2, 3, 4, 5 steps in order to get the oxygen group on. Now, before we design our synthesis, with the oxygen attached to the ring, it's an orthopara-director. With the ethyl group, it's also an orthopara-director. So somewhere along the lines here, we're going to have to add we're going to have to use the meta-directing group to add the other group before we convert it to the final product. In this synthesis, you could say, let's go ahead and add the acid chloride like we did the last time, and then convert that. That would give us the ketone, and then take the ketone and convert it to the alkane by either Wolff-Kishner or Clemenson. So we do have an alternative way to put the ethyl group on that would give us a meta-director. But we also have a meta-directing group in the nitro. So let's use that first. So let's think about the following synthesis. Let's say, okay, and again, if you want to stop and do this yourself, by all means do that, because you're going to have to do that when we have our exam. So in this case, let's put a nitro group on the ring. And then let's convert that nitro group. Well, let's not convert it yet because it's a meta-director. Now let's put the ethyl group on. So I only have to do one step there. So nitro would direct the ethyl group to the meta position. Now let's convert the nitro group to the NH2 group. Let's convert the NH2 group to the diazonium salt. Let's convert the diazonium salt to the OH. Too early for the O-. And let's convert now that phenol, the OH. Oops. Getting too close to the end. Now let's convert this OH group to an O- group. Now let's take that O- group, and I want to add an ethyl group to it, so I'm going to react that phenoxide with ethyl chloride to make the final product. And there's my ethyl group. Okay. So this would be a series of steps in order to accomplish this synthesis. Okay. Well, what about the reagents? So what reagent would I use? Again, you could go through here and add these in. We'd use HNO3, H2SO4 to add the nitro group. We would add CH3, CH2Cl, AlCl3 to add the ethyl group. We'd convert the no. What did I do? I missed a step. Or did I miss a step? Oh, here. All right. Again, if this was a top shelf operation, we would edit this part of the tape out, but I'm not going to. And again, I know it's not tape, I know it's digital, but so I'm going to take my benzene ring and put my nitro group on. I'm going to add my ethyl group here. Then I'm going to take my nitro group and convert it to my amine. And then convert the amine to the diazonium. And then convert the diazonium to OH with an H3O+. Deprotonate the OH, which means I could use anything. I could use hydroxide. I could use a C minus. I could use an N minus. I could use an H minus. I could use any of those reagents. And a good thing to think about would be, okay, where's the C minus come from? Grignard. Where does the N minus come from? NH2 minus. Where does the H minus come from? How about lithium aluminum hydride or sodium borohydride? And then this final step would be an SN2 reaction. That would be our Williamson ether synthesis. So is this getting more complicated? Yeah. Is it supposed to? Yeah. But to begin, what I'm also doing here is I'm kind of giving you some of the different ways that we can approach and reminding you of the reactions that you have to be able to accomplish these transformations. Okay, let's try another one. Oh my. Well, obviously it's getting more complicated. The question is, how do we put each one of these groups on the ring? So if you want to take a minute, think about that. Ester. How do we put an ester group on the ring? Okay. Now, for those of you who want to take the easy way out, you would say, let's do that. Yeah, no, that's not going to work. This is too unstable a molecule to work, so that is not correct. You will get no points for doing that on an exam or anywhere. So we have to think, how do we make an ester? I think there's a reaction that is named for someone called esterification reaction. And I think we've done it both in lecture and in lab. Fischer esterification. How does Fischer esterification work? You take a carboxylic acid, you react it with an alcohol in the presence of the acid catalyst. Great, so now I can make the ester. Except where did the carboxylic acid come from? Come on, Cortana, just disappear. Where did the carboxylic acid come from? Well, I think in an earlier slide we talked about that. Let's take the easy way out. Let's say it came from a methyl group. How'd the methyl group go on? Well, that's a piece of cake. Uh-oh, I don't know how to add this group. It's an alcohol. So let's do a little bit of review here and let's just think about this. What if I had a Grignard and I added to that Grignard this aldehyde? What would happen? And this Grignard is the benzene ring. It would come in, attack that carbon, and so what would I end up adding? I'd end up having a benzene ring attached to a CH with an O minus on top, a CH2CH3, so that then I could add my H plus to make the final product. So if you want to make an alcohol, easiest thing to do is to take a Grignard and add the aldehyde to it. I know we've just been doing Grignards with CO2, but we can't forget all of those other reactions that we learned this semester when we talked about Grignards. All right, so can we come up with a synthesis here? Now, actually, this could be a little tricky because of the sequencing. Let's see. Carbonyl group is meta-directing this carbon attached to the OH. While it's not directly on the chart, it looks like an alkyl group, so I would consider this to be orthopara-directing. So the first thing I should probably do is I should probably make the carboxylic acid and make the ester first, and then put the OH group on the ring. All right. So let's do this with a. Oh, I've got a really good idea here. Nope, I don't have a good idea. Let's just go ahead and convert the benzene ring to a bromobenzene. Or no, let's put a methyl group on. Let's oxidize the methyl group to the carboxylic acid. Now that's a meta-director. So now what I should do is now I should put the bromine on. Oh, I gave you the reagent. You should know that. So let's put the bromine on. All right, I need to think about this reaction right now. I need to seriously think about this reaction. Because if I try and make a Grignard out of this bromine, it's going to be deprotonated by the carboxylic acid, and it's going to kill it. So let's just go ahead and make the ester. So let's go ahead and react this with CH3, CH2, OH, and acid. Oh no, I gave you the reagent again. So let's make the ester. And now I've got the bromine. So now let's convert the bromine to... Nope. I shouldn't keep giving you the reagent. Let's convert the bromine to a Grignard. What? Oh, look, when I talk, I can have subtitles to this. No, sigh. Sigh. Okay, so what happened was that we made the ester, and there's a typo. And then we made a Grignard like we set up here. And then we reacted it with the aldehyde to give us the alcohol. So now what we just need to do is to add the reagents, and we will have a good synthesis. So that would be a completed synthesis. And at this point, I would accept that synthesis. Right? No, okay. Next problem. Three groups to add to the ring. How do we add the bromine? How do we add the nitro group? How do we add the aldehyde? Well, add to BR, what would we add? BR2 and FeBr3. How would we add the nitro group? Nitric and sulfuric acid. How would we add the aldehyde? Well, if you look at your chart, there is a Gatterman-Koch synthesis. Gatterman-Koch synthesis would be carbon monoxide, HCl, aluminum trichloride, and copper chloride. So we just have to get the sequencing right here to get the groups in the proper position. So let's think about this for a minute. I need a meta relationship between the bromine and nitro group, and I need an ortho para position between the bromine and the aldehyde. So what would our sequencing be? In order to get the bromine in the meta position, I'm going to need to add the nitro group first. Okay. Then, if I add the bromine, the nitro group is going to direct the bromine to its meta position. Now again, I'm drawing this structure because I want to put the groups in the proper position. Now if I did the Gatterman-Koch, the bromine is higher on the not Gatterman-Koch. Thank you. The bromine then is going to direct, because it's higher on the chart, to its ortho and para positions. Again, I just choose which one I want. Remember that it never adds in between meta positions. So that, in this case, I want the aldehyde to add in the bromine, in the para position, sorry. Okay. So now I could go ahead and do my Gatterman-Koch reaction. so that now it would add the aldehyde in the proper position. So now we just need the reagents. HNO3, H2SO4, bromine, and iron tribromide, and carbon monoxide, HCl, aluminum trichloride, copper chloride. Right, so adding 3 groups to the ring is doable, but it just requires us thinking about the proper sequencing of adding the groups. All right, we have 5 minutes left. So let me just jump ahead here. Oh, no, that was the last problem. How sad. So let's say that we wanted to do this problem with blocking strategy. So I want to add the bromine exclusively ortho to the ethyl group. How would I do that? Well, we know how to add an ethyl group. We know how to add a bromine. I want to use a blocking strategy to block the para position, and that group would be a sulfonic acid group. So, as I showed you in, I think, Monday's lecture, how would we set this up? Let's first add the ethyl group to the ring. Let's add the sulfonic acid group to block the para position. Let's then add the bromine. And the ethyl group is an activated group. The sulfonic acid group is a deactivated group. And, whoops. That would force the bromine into the para position. Para position. No, the ortho position. Then we would remove the sulfonic acid blocking group, and it would give us the ortho bromo ethyl benzene. Okay, so again, we just need these reagents. You can go ahead and try them. Okay. So what I've shown you in this lecture is that, our ultimate goal is to be able to take benzene and add groups to it in the proper sequence, so that we get the molecule that we're looking for. In order to do that, I first of all need to know my reagents and my reactions and my sequences to add certain groups like a carboxylic acid. All right, so these kinds of problems I will definitely ask you to do on the next exam. For those of you that haven't been watching or haven't been asking questions during the class periods, I have mentioned this, so I will now mention it formally, that I'm thinking that the next exam, what I will do is I will write an exam very similar to our previous exams. I will post it on the Canvas website, and then you can either print it out or handwrite it out, and I will give you 24 to 48 hours to complete the exam, and then scan it or take pictures of it and send it back via a Canvas Dropbox. And then I will grade it. I think that might be a little less stressful than trying to convert all of this to a multiple choice format that we're not completely comfortable with yet. Also, the ACS does not allow us to put their exams on a learning management system like Canvas. So the final exam will be multiple choice, but it'll be a multiple choice exam that I write, or that perhaps Dr. Kwan, Dr. Dowd, and myself write. So I'll have more on that. I know I originally had scheduled the exam the original exam was scheduled for Monday the 23rd. I asked you to keep the 27th open, but I might think and ask if you are amenable to moving that exam into the next week, simply because I heard that a lot of other exams got moved into next week, and I don't necessarily want to overload you. So I'll send out an email, and we'll either have it on the 27th, or perhaps I'll move it into a week later than that, just before Easter. Okay, if you have any questions, ask during the Zoom class periods, or on Piazza, or by email, or scheduling a Zoom meeting with me, either one-on-one or in a group, and we can go over whatever questions you have. I kind of like this subscripts, closed captioning thing. It's not completely accurate, but it's not bad. Okay, timer went off. Apparently the people next door have a bird that is going to mock that all night long. So all I'll be hearing is that beeping going off, because the bird likes to apparently mimic things. So it's going to mimic that timer. But that's the end of this lecture.